So today we're going to talk about the wave equation. And I will give away the punchline. Initially, we spent a lot of time in this class studying problems that looked like this. 0 equals uxx plus f of x, right? Or if you rearrange it, uxx equals negative f of x. And then we learned how to deal with this by taking a transform of this operator and the forcing function. And then in the last unit, unit 4, we ended up getting time derivative over here. But we had a very similar equation, and this was called the diffusion equation. And today, we're going to study a different type of problem, and lo and behold, we're going to get something that is quite similar, but it's going to have a second time derivative out front with, I suppose I should be real precise. These forcing functions can now depend on x and time. We're going to get a second time derivative out front instead of a first time derivative, and the resulting equation is going to be called the wave equation. And you can see we have this nice mathematical progression from no time derivatives to one time derivative to two time derivatives. And mathematically, these all kind of belong in the same class, all right? To solve all three of these, we have used the eigenfunction equation. Okay, and so this set of equations here form a family. Okay, they all have the same differential operator right here. But they all have slightly different structure. And the key to solving all of them is the eigenfunction equation, which I've written up top. And if you know how to solve the eigenfunction equation, then you can solve we can call this like a Laplace type equation. This is a diffusion type equation, and this is a wave type equation. And as long as you can solve the eigenfunction problem, you can solve all three of these. So that's kind of the big picture of really the whole class, all right, is that we're learning how to solve these three equations by solving this one equation. But for today, let me go back and talk a little bit about the wave equation. And we're going to first, as we did with the diffusion equation, we're going to derive the wave equation. And the physical context I'd like you to imagine is a string that is stretched. What are the significances of the coefficients C and D? So as we saw in the last set of lectures, the coefficient D is the diffusion coefficient called the diffusivity, and that affects the rate at which heat can move through a material. So it's related to the conductivity, but it also has to do with the specific heat and the density. And so a material with a high diffusivity would be something like aluminum, copper, silver, gold, that conduct heat very well. They have high conductivity and consequently high diffusivity. Materials with low diffusivity might be glass, air, wood, any kind of foam with lots of air stuck in it. As we'll see in this lecture, this coefficient here is going to have a different physical interpretation because this is a different physical context, and I'll save that for the moment when we get to it. So, no problem. Imagine a string stretched tight between two endpoints, and the string, whoops, the string has density Rho, which we're going to think of as a linear density. So it would be, kilograms per meter would be how we would measure that. Yes, it has a three-dimensional density, but the string is very small in two of the three dimensions. And so we would just collapse that onto like a linear measure of density. It has, what else? The whole string is under a tension. We're going to call that tau. And we're going to imagine what happens, if you pluck the string. So if you've played a musical instrument, you have encountered this situation. If you've ever picked up a guitar or play the violin or the harp or any stringed instrument, you have exactly this phenomenon where you have a string stretched tight, and you know that when you pluck it, it vibrates. And we're going to try and understand how that works. Okay, now, just like we did for the diffusion equation, we're going to first think about very fundamental physical principles. Now, when we were talking about heat diffusion, the principle that seemed to make the most sense was conservation of energy, that heat is a form of energy, and energy we know is neither created nor destroyed. It can be converted from one form or another, or it can move around, but it doesn't just spontaneously appear and disappear. And that allowed us to basically set up a bookkeeping statement involving some integrals. And then by the manipulation of those integrals, we were able to derive a partial differential equation. We're going to do exactly the same thing here. This is a very generic, a very universal approach to figuring out what the right governing equations are, is to appeal to these conservation laws. So it's no coincidence that I'm doing a very similar thing for the wave equation that I did for the diffusion equation. This is just how mathematical physicists figure things out. All right, so I'm going to do the same thing. I'm going to set up a little domain on this string, and just to give it a name so I can refer to it, I'm going to call it omega. And I'm going to write down an integral statement of an appropriate conservation law in this domain, or an appropriate, physical fundamental principle. And the fundamental principle I'm going to appeal to is conservation of momentum. All right, that momentum is neither created nor destroyed; it's conserved, and so the only way to change the momentum is with external forces. Now, another way to say that is through Newton's second law of motion, which is that mass times acceleration equals forces. And so really this is just the time derivative of momentum, right? So the time derivative of momentum, the only way you can change momentum is by the application of external forces, all right? So mass times velocity is momentum, the time derivative velocity is acceleration. So this is like the time derivative of mass times velocity equals sum of the external forces. All right, so let's figure out how to write this down for omega. Total momentum in the region omega is going to be the integral from A to B of density times velocity, right? And I'll go ahead and write that as V, density times velocity, dx. And so in principle, the momentum could depend on, or the density could depend on x. And so that's why it's not just, length of the domain times velocity of the thing. And the velocity could also, in principle, change as a function of x. You could have a wire behaving in such a way that one part of it is moving faster than another. I want to also, sorry, I've got a little bit of gunk in my throat this morning. We're going to be interested only in the vertical displacement of this wire, which we're going to call h of x and t. All right, so here's the x-axis. Z, we're going to say this is Z equals h of x and t, the displacement of the wire. And we're going to assume that the wire is not moving too much. It's not going to have like weird, huge changes in slope like this. And if you're familiar with a stringed instrument, you know, this is common. The string is much longer than the magnitude of the displacements. And the way that you can specify that is to say hx, we're going to assume, is significantly less than 1. Okay, so the string is vibrating, moving up and down, but not so much that the slopes approach 1. So v here, the velocity, is going to be dh dt, the up and down velocity. So anyway, this is the momentum, the vertical momentum in omega. All right, so this is total momentum in omega. All right, so that's how we started the diffusion equation. We wrote down an integral for the total amount of heat energy in omega. The next thing we did in the diffusion equation was we put a time derivative out here. All right, and just like there, this means rate of change of. So the rate of change of the total momentum in this little, why does that keep happening? In this little strip of string is what?
0, because it shouldn't change.
Well, momentum cannot be just created out of thin air. So that is one possibility. But what we really have to factor in is the sum of all the forces acting on this little piece of string. All right. And so there are two possible sources of force acting on our little piece of string, omega. Can anyone think of one of them?
Spring force, sort of elasticity.
Okay. So elasticity is what contributes to the tension. All right. The string is stretched tight, and so it would prefer to resist that tension. And so that's where you get this force. All right. So let's think about that. Let's think about that a little bit. Let's figure out how the tension affects omega. So we're treating this little piece of string, omega, as a unit. And as far as this unit is concerned, it feels stretched in two opposite directions, right? On this side, it feels stretched in that direction. And in this side, it's being pulled in this direction. And so what we need to do is add those two forces together. But we need to be really careful when we do that. And the key to figuring this out is to realize that when a string is under tension, it pulls in a direction tangential to itself. All right. So it's not just pulling left and right, it's pulling tangential to the string. So we have to figure out, and let me call this point A and this point B. All right. And what we're really going to need here is a force that has strength tau. And let's assume that it's constant tension. So it's constant tension tau. And then I'm going to write T hat of B plus tau negative T hat of A. All right. Because the tension in the right-hand side, if we assume that the tangent points to the right, which is the convention in the direction of increasing x, then this is going to be, this vector right here will be the tangent vector. This vector right here will be the negative tangent vector. This is strictly speaking the vertical displacement, so I don't really like this tangent notation. Let me kind of step aside and draw a little picture and figure this out. What is this? What is the sum of these two tensions? Imagine I have a string that's curved. I'm zooming in now, and I've got my little piece omega here. And here I have a tension force, and here I have a tension force. What is this vector? This vector is going to, if I imagine making a little triangle here, this vector is going to have, this hypotenuse will have a slope equal to the slope of the string at that point. And so I could draw a little triangle, and I could make this base have height 1, in which case this base would have height h of x. And so a tangent vector, a vector pointing in the right direction, would be 1 comma dh dx. However, that's not a unit vector, all right? And how do I make things into a unit vector? Does anyone remember from Calc 3?
Divided by its magnitude.
Divided by its own magnitude, which in this case is the square root of 1 plus hx quantity squared. And then I could go over here to this vector, and this vector is going to point in the direction -1. If I draw a little triangle here. And negative hx, and again, its magnitude is going to be 1 plus hx squared. Now, the only difference in these two, it looks like they're exact opposites, but we have to remember that this one is being evaluated at the point B, and this one is being evaluated at the point A. Okay? Now, the other thing I want to help us remember is what was one of our assumptions. Our assumptions was that the slope is not very big, right? It's much smaller than 1. The string is not wildly oscillating. And so in this denominator here, hx squared is much, much less than 1. And so we'll neglect this term right here, in which case the denominator just becomes 1. And so the way I'll write that is I'll say that's approximately just -1 minus hx evaluated at A. And this right here is approximately 1 hx evaluated at B. Okay, under that small slope assumption. Oh, wait, that's what's going on. Okay, and if I now sum these two forces, right, I have a tension force on this side that's tangential to the string, and I have a tension force on this side that's tangential to the string. And they're about equal to these two things. If I add them together, okay, I get 0 because the lateral components cancel. 1 and -1 add up to 0. But then I have here hx evaluated at B minus hx evaluated at A. All right, and so that is, I should say times tau, the magnitude of the tension force. Okay, and so if I go back up here, I can replace this with just its vertical component, right? And the vertical component of the tension forces is given by tau hx of B minus hx of A. All right? So those are those two tension forces, and those are the most important forces acting on the string. Can anyone think of any other forces that might be acting on the string?
Perhaps the pluck that set it into motion.
That would give it an initial position and an initial velocity. So it's very good to recognize that we need to factor that information in. That will end up coming in the initial conditions of the problem. Think of a force that might be relevant. Gravity, right? Unless you're playing your instrument in space, you might have a small contribution due to gravity. It's probably much smaller than the contribution due to the tension. The tension is usually pretty large. Gravity is not all that large compared to that tension force. But just for completeness, let's assume that we might have external forces. And again, just for total completeness, let's assume that those forces might vary with space. And so to get the sum of all those forces, we might have something that looks like this. Okay, so this is sum of tensions on each side of omega. And this is total external forces, body forces. Okay, so here I go. I have an equation now. And this equation looks to have a very sort of similar form to the equation that we had the other day when we were studying the diffusion equation. We had an integral, a time derivative of a spatial integral here on the left, and then we had a sum of two things, one on each side. In the diffusion equation case, it was the flux on the right minus the flux on the left. Here in the wave equation case, it's the tensions, the vertical component of tension on the right-hand side minus the vertical component of tension on the left-hand side. And then we had external contributions, external heat sources in the case of the diffusion equation because we were concerned with conservation of energy, external forces in the case of the wave equation because we're concerned with conservation of momentum. What can we do with any of this? This is just like the diffusion equation. It is a, let me try something here. Let me highlight this and copy it and then start a new page and paste it. Okay, just like the diffusion equation, this is an accurate statement of conservation of the quantity we're interested in, conservation of momentum this time. But also like the diffusion equation, like the equation that we derived last time, it's kind of unwieldy. I have the derivative of an integral equaling a sum of things. It's just like this big mixture of lots of different types of mathematical objects. And so can anyone remember what we did to make progress and simplify that last time? There were two important things that we did. All right. I don't see any suggestions. The first was we had here a integral in time of, yes, we combined all the integrals, but this isn't an integral. And so that's of limited value at the moment. One thing we did was we said, okay, we have an integral in space and a derivative in time, and time and space are independent variables. And so we actually saw this come up again when we were talking about the transform of the time derivative. It's the same principle, and we used it when we were deriving the heat equation. We can interchange the order of those operations. We can effectively pull that time derivative inside the integral as long as we make it into a partial time derivative, because inside the integral, the space variable still exists. And so if we're only talking about a time derivative, it needs to become a partial derivative. That's called Leibniz's rule. Leibniz's rule. Okay, this becomes the integral from a to b of the partial derivative of rho v dx. And then, does anybody remember what we did with this? it is the difference of hx on the right-hand side minus its value on the left-hand side. And this sort of formulation should, at least once you get in the habit of recognizing it, it should look a little familiar. You've definitely seen that. Yes, we can rewrite that. Does anybody remember how we can rewrite that or why we can rewrite that? Yes, yes, it is. We can use the fundamental theorem of calculus. All right, and we can rewrite that as the integral from a to b of the derivative of hx dx. Okay, which is indeed the integral of hxx. And then finally, this can remain as it is. It's already an integral from a to b of some external forces, dx. And so having used Leibniz's rule on the first term and the fundamental theorem on the second term, I now have all of my terms are integrals. And so I can combine them all into one big integral. Integral from a to b of the time derivative of rho v minus tau hxx, simplifying that term, minus f dx equals 0. And here, I want to save myself a few minutes to talk about some boundary conditions. So I'll speed it up a little bit here. If this whole thing equals 0, the thing we have to now remember is that this statement that we have obtained is not dependent on the values of a and b. Okay, I just selected at random a left-hand boundary and a right-hand boundary, a and b, and I began writing down things that would have to be true in that domain. But this statement does not rely for its truth on the values of a and b, and so it's true for any combination of a and b. And the only way that can be true is if the integrand itself is identically 0. Because if the integrand were not 0 somewhere, you could choose a and b on either side. Suppose that integrand, were 0 almost everywhere, but then it was like non-zero in some place. Well, then you could choose a and b right here and invalidate that statement. All right. And so if this statement is truly to be true for any choice of a and b, it must be true that the integrand itself is 0. And that gives us, I'm going to assume that rho is constant in time. Rho is not, the density of the wire is not changing in time. And so I have here rho, and then what's dv dt? V is the velocity, that's the derivative of position. So this becomes the second derivative of position. Okay, and this is called the wave equation. All right. Now you can rewrite it, divide through by rho is sort of conventionally done. You can say h tt equals tau over rho h xx plus 1 over rho f of xt. And then if I rename this quantity c squared, I will get htt equals c squared hxx plus, and then I can call this little f of x and t, where c equals the square root of tau over rho, and little f equals big F over rho. All right, and here I have my wave equation that we wrote up at the top. What is c squared? C squared is just this constant right here. It's the tension divided by the density. The higher the tension, the higher the value of c squared. The higher the density, the lower the value of c squared. And we'll talk about what this means physically, higher or lower values of c squared, in another class. What I want to spend the last 10 minutes talking about are boundary and initial conditions. Oops. Okay, so let's again draw a little spatiotemporal diagram to help us understand the domain of this problem. All right. So again, we have two time derivatives. Or sorry, we have two space derivatives right here, just like always. This time we also have two time derivatives, right? So that's one more than we had before. We've had two space derivatives all class long, and we're dealing with a finite domain. And so it might not surprise you that in response to these two spatial derivatives, we're going to need two boundary conditions, and that we're going to put one on either side of the domain. What's new here is that we're going to have a need for two initial conditions. All right. So just like before, we have a boundary condition on the left, which can depend on h and hx. Then we're going to, sorry, that goes on the left. And then we're going to have a boundary condition on the right. But we're going to need two initial conditions down here, and I'm going to call them, we're going to have one on the value of h. So this is just like ODEs. We have the value at time t equals 0. We're going to call that I0 of x. Oh, and these can in principle depend on time now. As suggested by this diagram, they live along this axis here, and so they can change in time. Okay, and then we're going to have a second initial condition on the initial velocity. So we have the initial position and the initial velocity. And Wade, you mentioned the effect of the initial pluck, and that's where this comes in. So if I pull the string and then I hold it steady and then I release it, I will have an initial displacement that is non-zero, but I will have an initial velocity that is 0, right? If I lift up the string and I hold it steady before I let it go. On the other hand, that would be, like a harp that you pluck, you move it, and then you let it go and you pluck it. On the other hand, I could have a situation where the initial position is 0, but the initial velocity is non-zero if I suddenly hit the string with something, which you can encounter in one of my favorite instruments, the hammer dulcimer, where you just kind of hit it with a hammer and you impart a little pulse of velocity. Would be a good way to model that. The initial position of the string is at rest. You hit it with a hammer, all of a sudden you give it some velocity and it responds.
So it's like most of the percussion instruments.
Yeah, a percussion instrument would have, you could model in a very similar way. A drum, for instance, has a membrane that obeys the wave equation in more than one dimension. And you hit it with a mallet, imparting some initial velocity. So the initial position and the initial velocity are fairly easy to describe what's going on. what I want to spend some time talking about is the interpretation of the different boundary conditions. So like in any boundary value problem, you can have three mathematical types of boundary conditions. Okay, so you can have h equals a constant. Okay, and this is not too hard to interpret. This simply says that the position of the string is fixed, and the most common are going to be homogeneous boundary conditions, where h equals 0. And so if h equals 0 on both ends, it's like the string is simply attached to a common position at either end of the domain, right? And this is sort of the typical case. The most typical set of boundary conditions for a stringed instrument is that you have homogeneous Dirichlet boundary conditions, and the string can vibrate up and down in between, but it always has to remain fixed at those endpoints. Okay, you could imagine some geometry, where one or more of the boundary conditions is non-zero. You could have a string, stretched between two positions at some elevation from 0 if you were so inclined. I don't know, imagine you're dealing with like a gondola or something. You're going up a mountain, and you've got these
I see what you did there. If you're so inclined.
I didn't even realize that. No pun intended. We should just stop lecture right there. So the second type of boundary condition is Neumann boundary condition, where you impose a slope, or more frequently, you impose a zero slope, just like in the diffusion equation. The most common version of these boundary conditions, especially the Neumann condition, would be a zero value here. That is a little bit harder to interpret. If we go back, what we find is that zero slope, where does the slope come into our model? Way back. The slope comes into our model actually over here. When we're physically figuring out what the different things correspond to, just like how in the diffusion equation, the slope of the temperature field had a physical interpretation, it was related to the flux. When we're doing wave equation modeling, the slope of the string corresponds to the vertical component of tension. All right, it's the up or down force imparted by tension is proportional to h sub x, the derivative of h. All right, and so what does it mean to say that that is 0? I mean, geometrically, it means that the string is flat when it reaches the endpoint, but it doesn't mean, it does not constrain the value at the endpoint. It means that the string can move up and down the left-hand side. It always has to remain flat. And physically, what that means is that as it moves up and down, the vertical component of tension has to be 0 at all times. And so it turns out there is a way to interpret this. Okay, mathematically, it is what it is, and it's fine. What might it mean physically? It's pretty weird, but you can assign it a physical meaning. And it would be, suppose you have a string that is attached to a metal pole, but instead of being like welded to a pole, all right, which would be a Dirichlet condition, imagine that it is attached to that pole by a hoop. And this hoop can move up and down the pole without any friction. All right. And so if that's the case, if there's no friction, then there will never be a vertical tangential force at that side of the domain. All right. And so this is the physical interpretation of Dirichlet, a Neumann boundary condition. Like I said, it is a little bit weird. And this brings up kind of an interesting point that not everything that is mathematically possible is physically common. All right. So for the wave equation, by far the most common boundary condition, especially when we're talking about string instruments, are Dirichlet conditions. And yeah, you can make up some meaning for a Neumann condition, but it just doesn't really matter because you don't really encounter that very often in real world. Now, that doesn't mean I won't give you a homework problem that involves such a fictional situation to test your understanding of all the mathematical concepts, but it's worth keeping in mind that just because something can exist mathematically doesn't mean that it's very common. And finally, we have like our Robin conditions. HX, you could have like alpha HX plus beta H equals C, or I guess if I were being really organized here, I would say alpha H plus beta HX equals C. Again, the most common version of this would be a homogeneous version where, let me just say, for example, HX is proportional to H. And this is even weirder. Again, you can assign a physical meaning to this, but what it would mean in this case is you have a hoop, a frictionless hoop attached to a pole, attached to a spring, which is welded to some location on the pole. And so it moves up and down, and there's no friction, there's no vertical component of tension that comes from the string itself because of the frictionless hoop, but you do have the spring, and the farther I move away from zero, the more the spring is pulling back on the hoop attached to the string. So it gets pretty ridiculous. But again, some sort of meaning can be ascribed to these type of boundary conditions as well. And it's worth sort of having in mind what these things mean so that if you do encounter such a boundary condition, you know what it means, you know what to expect. We saw this when we did the heat equation. If you encounter a boundary condition in the heat equation that says ux equals 0, you know that that means that heat cannot pass through the boundary, that this is an insulating boundary condition. And so that can help you check and see if your solution is behaving in a way that you expect, right? If you look at it and you can see that heat is leaving the domain through this boundary, then you realize you must have done something wrong because this mathematical boundary condition has a physical interpretation that you can apply to your solution and see if it makes sense. All right, so that's all for today. It's 11:50. As always, I'll stick around and ask questions if you have them, but you're free to go. I will post solutions to homeworks 3 and 4 shortly. Again, this material on the wave equation will not be on the exam. I will also have extended office hours tomorrow for any exam questions that you may have. Let me say, I don't know, about 10 to 2. The exam will be in our regular evening exam slot from 6 to 7:30. Those, will you be available after class? Yes, I will. The exam will be from 6 to 7:30. Those open note, yes, because of the coronavirus quarantine, we're having to make adjustments. So not for 4. I will post what I have for 3. They're not like perfect, but I'll post what I have for 3. And I don't have any for 4. Although, what I can do is I can post my my written notes, which are not as neat, but I can do that. Will I be sending Zoom links? It will be in this room. It will be in this Zoom link. I know I've made arrangements with, yes, similar to the first test in length and difficulty. We use Zoom. It's in this channel. Exam, no, not at 6:30, at 6 o'clock. 1 or 2 of you have, yes, I will post it online, and you don't have to print it out if you don't have a printer, although you're welcome to if you want to. I'll post it like 5 minutes or 10 minutes before, and if you want to use that time to print it out, that's fine. Otherwise, you can just do the problems on regular paper, And then when the exam's over, just, take pictures with your phone and upload them to Canvas. And that's how we'll do it. Just like how you turned in the homework. Yes, I'll post the homework solutions very shortly. Oh, tomorrow. The exam is tomorrow. Yeah. Yep. No problem. You are welcome to, if that's how you'd like to do it. Yep, that's no problem at all. Have all the notes. Yes. No, the only one that's not uploaded are today's, and I can upload those, but that's not on the exam. So all the notes for 3 and 4 have already been uploaded. It's possible that I forgot to upload the last one, but I thought I remember doing it. I'll double check. All right, you too.